Esteemed colleagues, distinguished members of the scientific community, and ISWTA 2025 Congress, it is my privilege to present our recent investigation into solar energy forecasting paradigms within the Ecuadorian highlands. The research I shall elucidate today is encapsulated in our paper, Solar Energy Forecasting Using LSTM, a comparative analysis with photovoltaic data from Cajas National Park, Ecuador. This collaborative endeavor unites expertise from three premier Ecuadorian institutions: the Institute of Micro and Nanoelectronics at Universidad San Francisco de Quito, the Departments of Computer Science and Electrical Engineering at Universidad de las Fuerzas Armadas ESPE, and the Department of Computing Science and Industry at Universidad Católica del Maule in Chile, alongside industrial partnership with INH Tech. Our corresponding authors, Marco Flores Callero, have orchestrated a multidisciplinary team comprising Diego Guevara, Alexandra Corral, Marcelo Cabezas, Anderson Salazar, Felipe Jaramillo, Lucio Paucar, Kevin Navarro, Josué Herrera, Alberto Albuja, and David Zavala Blanco. This confluence of academic and applied research perspectives has yielded findings that we believe constitute a substantive contribution to the epistemological corpus of renewable energy forecasting. El Cajas National Park, Ecuador. Let us first situate our study within its geographical locus. El Cajas National Park, a páramo ecosystem of exceptional ecological significance, resides in the Andean highlands, proximate to Cuenca, Ecuador, at altitudes ranging from 3,100 to 4,450 meters above sea level. This topographical configuration engenders a unique meteorological regime characterized by high-altitude solar irradiance and pronounced thermal amplitudes, with diurnal temperature oscillations spanning from -2 degrees Celsius to 18 degrees Celsius. The strategic import of this location for photovoltaic deployment is corroborated by the Solar Atlas of Ecuador's National Institute of Energy Efficiency and Renewable Energies, which quantifies the insolation potential at 4.5 to 5.5 kilowatt-hours per square meter per diem. Such irradiance levels, coupled with the correlative thermal coefficients favorable to silicon-based photovoltaic modules, position El Cajas as an optimal candidate for utility-scale solar generation. Notwithstanding this latent potential, Ecuador's exploitation of its solar endowment remains nascent. A mere 31 megawatts installed capacity as of 2023, according to the National Electricity Operator, against a theoretical potential spanning several gigawatts. This chasm between potential and actualization forms the empirical backdrop against which our predictive modeling framework has been developed. The park's climatological idiosyncrasies, specifically its dynamic interplay between solar radiation, temperature differentials, and orographically modified wind patterns, necessitates sophisticated temporal modeling approaches that transcend conventional statistical forecasting methodologies. The problem of the energy crisis in Ecuador. The exigency of our research is inextricably linked to Ecuador's recent energy crisis, a multifaceted systemic failure that manifested during two distinct periods, October 2023 through April 2024, and subsequently from October to December 2024. An extreme meteorological drought precipitated by the El Niño Southern Oscillation phenomenon precipitated a catastrophic reduction in hydroelectric reservoir flow rates, attenuating generating capacity by approximately 1,900 megawatts. This deficit was particularly deleterious, given that hydroelectric infrastructure constitutes over 70% of the nation's electricity matrix, rendering the system acutely vulnerable to hydrological variability. Compounding factors exacerbated the crisis: insufficient thermoelectric redundancy,
limited cross-border interconnection capacity with Colombia, and the suspension of energy imports due to regional supply constraints. Consequentially, Ecuadorian citizens endured power outages extending to 14 hours per diem, engendering economic losses exceeding 3.6 billion US dollars and necessitating the proliferation of diesel-fired emergency generation with concomitant environmental externalities. This systemic fragility underscores the criticality of energy diversification through renewable vectors that exhibit non-correlated intermittency profiles. Photovoltaic generation emerges as a strategic panacea, not merely by augmenting installed capacity, but by providing diurnal generation peaks that partially offset hydroelectric nocturnal deficits. However, the stochastic variability inherent in solar irradiance, driven by cloud transients, aerosol optical depth fluctuations, and seasonal declination variations, imposes significant challenges for grid operators in maintaining supply-demand equilibrium and minimizing spinning reserve requirements. Our research posits that accurate short-term forecasting, underpinned by deep learning architectures, constitutes the sine qua non for seamless photovoltaic integration into Ecuador's beleaguered electricity grid. Solar Variables database of Cajas National Park comprises a meteorological dataset procured from Cajas National Park, encompassing the temporal domain from June 2020 to March 2024. Data acquisition occurred at a sampling frequency of 6 measurements per hour, yielding a granular spatiotemporal resolution requisite for capturing subdiurnal variability patterns. The multivariate parameter space includes ambient temperature, relative humidity, wind velocity vector magnitude, atmospheric pressure, precipitation intensity, and global horizontal irradiance. Figure 1 elucidates the temporal evolution of these variables, revealing several salient features warranting exegesis. Panel A evinces a modest secular warming trend potentially attributable to anthropogenic climate forcing. Panel D manifests an anomalous irradiance spike during 2021, which we attribute to sensor miscalibration or data acquisition system artifacts, necessitating subsequent outlier excision. Panel C demonstrates initial precipitation abundance succeeded by a regime of reduced pluviosity consistent with the observed drought trajectory. Our correlational analysis, summarized in Table I, reveals that solar radiation exhibits statistically significant positive correlations with temperature, R equals 0.8111, and wind speed, R equals 0.6035, whilst manifesting a robust negative correlation with humidity, R equals negative 0.7940. Crucially, pressure and precipitation evince negligible correlation coefficients, substantiating their exclusion from the feature vector to mitigate aleatoric noise and attenuate model complexity. The pre-processing pipeline adheres to rigorous protocols. First, irrelevant variables are ablated. Second, null values undergo linear interpolation to preserve temporal continuity. Third, outlier excursions exceeding 3 standard deviations are truncated. And fourth, min-max normalization rescales all features to the 0.1 interval, thereby ameliorating LSTM sensitivity to scale disparities. The resulting sanitized dataset is partitioned into training and validation subsets via an 80-20 stratified split that preserves seasonal and diurnal periodicity, ensuring robust out-of-sample performance evaluation.
Long short-term memory networks, similarly proposed by Hawkwriter and Schmidt-Huber in 1997, constitute a specialized recurrent neural network architecture designed to ameliorate the vanishing gradient pathology endemic to vanilla RNNs. The architecture incorporates a memory cell state regulated by 3 gating mechanisms: an input gate modulating information ingress, a forget gate controlling retention versus erasure of historical context, and an output gate determining egress of the hidden state. These multiplicative interactions implemented through sigmoid and hyperbolic tangent activations, endow LSTMs with the capacity to capture long-range temporal dependencies spanning hundreds of time steps. For solar radiation forecasting, where diurnal cycles, seasonal declination, and weather system evolution manifests across disparate temporal horizons, this ability to model nonlinear sequential dynamics with extended memory renders LSTMs particularly apposite. LSTM architectures, configurations, and models. Our experimental design systematically interrogates 10 distinct LSTM architectures, each configured with the atom optimizer and mean squared error loss function. Models 1 through 4 establish our baseline configurations. Model 1 employs a two-layer architecture with 60 and 25 neurons, hyperbolic tangent activation, a dropout regularization rate of 0.3, a temporal lag of 1 step, and 20 epochs of training. Model 2 replicates this topology but substitutes ReLU activation to evaluate convergence acceleration. Model 3 introduces a 3-step lag and learning rate attenuation to 5 times 10 to the negative 1, whilst reducing neuron count to 50 and 25. Model 4 expands capacity to 150 neurons, maintaining TAN activation and 3-step lag with eta equals 10 to the negative 3. These initial configurations serve to probe the sensitivity of forecasting accuracy to network depth, parameter cardinality, and activation nonlinearity, establishing a performance baseline against which more sophisticated architectures can be benchmarked. LSTM architectures, intermediate refinements models. Progressing along the complexity spectrum, Models 5 through 7 incorporate enhanced temporal context and regularization strategies. Model 5 increases lag to 5 steps, a configuration we hypothesize would capture diurnal periodicity more effectively, whilst employing 50 neurons per layer, TAN activation, and 25 epochs. Model 6 represents a pivotal architectural augmentation, a 3-layer stack comprising 75, 50, and 25 neurons with return sequences enabled, facilitating hierarchical feature extraction across temporal scales. Trained for 75 epochs with 5-step lag, this configuration achieves profound representational capacity. Model 7 introduces batch normalization layers interposed between each LSTM stratum and dropout, utilizing 64, 32, and 16 neurons with p equals 0.2 to mitigate covariate shift and accelerate convergence. These intermediate models thus investigate the trade-off between architectural depth, regularization efficacy, and temporal receptive field extension. LSTM architectures, advanced topologies, and hyperparameter synthesis. The final architectural cohort, models 8, 9, and 10, explores high-capacity topologies and extended temporal lags. Model 8 concatenates batch normalization with a 100, 50, 25 neuron hierarchy, 2-step lag, and reduced dropout. Model 9 mirrors the structure but increases training duration to 50 epochs with 3-step lag. Model 10 culminates our experimental matrix as a deep 3-layer architecture with 256, 128, and 64 neurons, batch normalization, p equals 0.3, and a 7-step lag, the most extensive temporal context evaluated. Across all 10 configurations, hyperparameter optimization proceeds via systematic grid search, with evaluation metrics comprising mean absolute error, mean squared error, Pearson correlation coefficient, and coefficient of determination. This methodological rigor ensures parsimonious identification of the architecture best suited to quasi-periodic statistical processes governing solar irradiance in mountainous terrain. Results. performance metrics and model selection. Our empirical results, consolidated in Table 2, unequivocally demonstrate Model 6's superiority, achieving a mean absolute error of 0.0107, mean squared error of 0.0002, correlation coefficient of 0.9955, and coefficient of determination of 0.9981. This architecture manifests exceptional predictive fidelity. The learning curve, depicted in Figure 3, evinces rapid loss attenuation during initial epochs, stabilizing asymptotically around 0.01 without divergence between training and validation trajectories, indicative of robust generalization and absence of overfitting. Comparative analysis reveals that both insufficient and excessive lag values degrade performance, corroborating our hypothesis that optimal temporal context is critical. Furthermore, neuron count per se does not guarantee superior accuracy. Rather, extended training duration and hyperbolic tangent activation emerge as pivotal determinants of forecasting prowess. Model 6's three-layer 75-50-25 neuron configuration thus represents the Pareto optimal balance between representational capacity and computational parsimony. Conclusions and future trajectories. In summation, our investigation substantiates three principal conclusions. First, rigorous feature selection, retaining temperature, humidity, and wind speed whilst discarding pressure and precipitation, enhances signal-to-noise ratio and model robustness. Second, LSTM networks, specifically Model 6's architecture, demonstrate remarkable proficiency in capturing the nonlinear, non-stationary dynamics of high-altitude solar radiation, achieving R² exceeding 0.998. Third, these predictive capabilities translate directly into operational benefits for Ecuador's grid operators, enabling precise short-term generation forecasts that optimize dispatch scheduling, minimize spinning reserves, and attenuate renewable curtailment. Future research trajectories will encompass hybrid CNN LSTM architectures to exploit spatial-temporal correlations, integration of satellite-derived aerosol and cloud optical depth data, real-time implementation on edge computing platforms, geographical scalability across Ecuadorian microgrids, and computational optimization through quantization and pruning. We contend that this work establishes a methodological blueprint for enhancing energy sovereignty and grid resilience in regions characterized by acute hydroelectric dependency and burgeoning solar potential. I thank you for your attention and welcome substantive discourse on these findings.